Welcome everyone to this latest AS2 webinar on testing the right path well with Rob Sabourin. Rob has, so I've known Rob, I met him years ago actually. I think it was in Orcas Island for James Bach's Rapid Testing Applied. I think we chatted for a little bit. I also met him again at What's It, which is the workshop on teaching software testing with Kem Kaner and Becky Fiedler in Florida many years ago. I've also attended a number of his workshops and conferences. So Rob is fairly well known in the testing community. He's been at CAST many times. He is a board member for the Association for Software Testing. He's got more than 36 years of management experience leading teams of software development professionals. Frequently speaks at conferences. He's a adjunct professor of software engineering at McGill University. He also serves as the principal consultant of Ambibug.com. And so how's that for an introduction, Rob?
Excellent. That's a really nice one. I've got to remember that one. Some future engagement.
All right. So it's all you now. Take it away.
All right. Yep. Thank you very much, and welcome to, I guess, my short webinar called Testing the Right Path Well. And I call this a test design story. I'm starting to figure sort of types of stories I share. And this is a story about a real problem that happened at a customer of mine in Chicago. And there's actually been some publications about this and articles written about this. Although today I will anonymize a little bit parts of the story. I think if you dig a little bit, it won't take too long to find out a lot of details about this that have been published by different people at different times. In either case, it's a test design story. And so that's me, my bio. Take note of my email address. If you have questions and stuff afterwards, if you want to get in touch with me, just drop me a line at my email address. rsabourin@ambibug.com is a great way to get a hold of me. And I know that sometimes people think of a really good question a few days later and they wish they had asked it at the time. Well, don't hesitate. You can always send me a line and throw me a question. I'm glad to answer about whatever you want to talk about. But I guess supposedly mostly about the subject of this little webinar of ours. So to begin with, when I talk about testing, I want to use a metaphor. And the metaphor I use when I talk about software testing very often is the Swiss Army knife. And for me, the Swiss Army knife is a metaphor for all of the different choices we have in choosing what to test and how to test what to test. And if you look at a Swiss Army knife, you'll see that there's a lot of different blades for a lot of different purposes. There's no sort of one blade that solves all your problems, and maybe sometimes there's too many blades for you to figure out. But a good, well-designed Swiss Army knife has a bunch of blades that the person who holds the knife can sort of figure out based on factors around them what might be the most appropriate blade. And to me, this is exactly what we're facing with testing. So as you're testing software, think of things like test design approaches or test ideas as sort of blades of a Swiss Army knife. It's really cool because my presentation seems to always want to automatically jump ahead a slide on me here. I don't know why, some sort of timing flag in PowerPoint. So I think about the Swiss Army knife as my metaphor for test design. I encourage people to learn as many test design techniques as they can, and to not just learn them, but to practice deciding which technique is appropriate in which context. So there's a lot of context factors involved. Now, testing itself is an intriguing domain. It's something that's been around for a while, I guess. Software testing, probably the first book about software testing was actually published in 1979. And we can argue that it's a fairly new field. And we know just a little bit about it. If you want to know, what do we really know? We're just beginning in the field of software testing. We haven't been doing software testing for 2,000 years, like civil engineers and architects. For us, it's a fairly new space. And what's exciting to me about it is that we're surrounded by a lot of turbulence. Everything is changing around us. It's the projects are changing, the technology's changing, the people are changing, the tools are changing. So the methods and techniques are sort of fighting to keep up with the changing and technologies around us. And yet we still are in a very young field that we know very little about. One of the few things we know about software testing comes from the work of Edgar Dijkstra. Now, Edgar Dijkstra is a pioneer in applying discrete mathematics to software engineering problems or computer science problems. Dijkstra in the 1960s found out how to solve problems with computers like the traveling salesman problem, which today is the fundamental method used in tools like Google Maps and Waze and all the sort of cool map searching technologies and methods. So Dijkstra invented the method to solve that with computers. Dijkstra invented modern structured programming. He invented that, which led to today object-oriented development, which is the dominant approach to software development. And he basically applied discrete math to the problem of software testing. Dijkstra's principle is about the only true law we have in software testing. And it's something that I think describes the nature of software testing. Dijkstra says that program testing can be used to show the presence of bugs, but never to show their absence. We cannot demonstrate by testing that a piece of software is bug-free. And indeed, because of this principle, and this is one of the few things we know about testing, because of this principle, we sort of have a few conundrums. There's a conundrum or two in testing. For example, testing is intractable. Even the simplest feature has an infinite number of possible test cases. And this is actually true. If you start looking at the complexities of testing things, look at the combinations. They multiply and multiply and multiply. And the more options you have, the more combinatorics. It's huge. The number of possible tests for even the simplest feature is infinite. And this is scary, because that means that complete testing is impossible. So this is depressing, as management wants us to tell them something about a product. They want us to sort of say, hey, we tested it and we know something. We've tested it completely. So this is basically the intractable nature of testing. Complete testing is impossible. But for me, this is a joyous thing. This is a wonderful thing. This is fantastic news, because the good news here is that there's always another way to test something. So we have these three problems, right? We have an infinite number of possible tests, we have complete testing being impossible, and we have always another testing idea. And this third one is the one that I love to use the most, because whenever I'm stuck in a testing problem where I have ridiculous odds against me, I sort of stop and I say, well, there must be another way to test this. There must be another perspective to test this. And figuring out the other things depends on a few factors, like we call these context factors. And I've mapped a lot of context factors in my time, and I see them generally breaking down into what I call four categories of factors. So there's the factors related to business. Why are we doing this product from a business perspective? How does this help us make money? How does this help our customer achieve their goals? So what are the business factors? And then we have technological factors. What sort of tools are we using? Are we making the product ourselves? Are we buying it from other people? Are we integrating things? What type of technological factors there are? So business factors help us understand more about what's important for our business. Technological factors help us understand what can go wrong or what can screw up. And then there's organizational factors. And organizational factors help us understand how our testing work fits into life cycles, like when are we going to do what, and who's responsible for what part of the delivery chain, and what is maybe the responsibility in terms of focus and scope at different times in different places. So we look at business factors, technological factors, organizational factors, and there's also, not on this map, but equally important, cultural factors. And the cultural factors are, to me, devastatingly rich and complex, and yet very hard for me to quantify and imagine how to describe to you. I just know that it depends on your social and familial culture, how you organize yourself as a team, how you share information, that will influence how you focus your testing. So many factors influence basically what we should focus on, and what we should focus on helps us decide which blade to choose, right? Helps us decide what testing approach is the best one. Now, I'm not going to go through 50 or 100 different blades in test design, because today I want to talk about one, which is the blade called control flow test design. Now, control flow test design is a method of test design that's been around for a while. It's a method of test design that can help us find out, for example, how to test code, because code has a lot of different pathways through it. Control flow test design can help us choose what are the interesting pathways to test in our code. Data paths through a system. What are the different data paths we can exercise? Transaction flows. What are the different ways transactions can pass through our system? Any business process flows. Anything that has pathways can be tested with control flow test design. Control flow test design, if you look at it, can help you understand, for example, the principles of navigating a city through a map. If you look at this as a sort of a sketch of the map of London, and look at how many roads and routes there are. Imagine if you want to start at one point and get to another point. So you want to go from, Islington to Westminster. And you sort of say, okay, well, from Islington to Westminster, how many different pathways there are? And of course, if you look through this map, you'll probably see just linear paths through. There's probably hundreds and hundreds of them. And if you include looping allowed, there's an infinite number of pathways through this. Well, this is very, very similar to a software testing problem when you have a lot of choices to take in deciding what functions you operate, in what order, or what data to use in what order, or what features to use in what order to get a job done. And there's basically, especially if you allow looping, there's an infinite number of ways to do it. So control flow test design helps you find a reasonable subset of the paths through a system. And we say a reasonable subset. We don't want that perfect set that gives us perfect knowledge. We want something that's reasonable. And that reasonable set, we can define it. Maybe different people think different things are reasonable, but in my experience, when I don't have time to test every path, I probably want to test a subset of them that has certain characteristics. Like maybe I've tried, at every intersection, each way I can go at least once. I've tried each segment of road at least once. And I know that if I take the paths that I've tried, I can combine them to create any path through the system. To me, that sounds like a pretty reasonable subset to try. So there's all sorts of networks. This is the topology problem of the subway system in London. There's so many paths, so many ways to get from point A to point B. So which ones do we test? Now, the field of software testing, as I mentioned, has been around for a while, but our first book in 1979 by Glenford Mayer talked about control flow testing. And this is published in 1979. And in the book, control flow testing is described, but unfortunately, it was described as what is known as a white box technique. A white box testing technique is a technique that's generally reserved for people who are testing code. You're looking very low-level design, and you're trying to figure out how do you do low-level design testing. And of course, people like to look at the code, and because code has a lot of pathways through it, they want to say, well, we can't test all pathways, so what is that cool subset of the pathways that we should exercise? So this old book on software testing, right, that old wisdom was written for programmers. Now, Unfortunately, at least two major international standardization organizations, I'll name them, the ICEP group and the ISTQB group, have classified control flow testing as a white box technique and includes it in their syllabus so that it's taught to people as if it was really for people doing white box testing. I would argue that that does a disservice to the path approach, because path analysis can be used to test any system that has a lot of pathways through it, not just code. So I'm trying to help people learn how to apply control flow testing to systems that aren't necessarily all code. Now, how do you do control flow testing? Well, you have a problem. You have a problem like one of these maps here. You have a problem. And the first thing we do is we create a type of diagram called a control flow diagram. So we create a control flow diagram. And then once we've got that diagram, we use an algorithm, and I'll show you an example algorithm, to find a set of paths. The set I look for, I usually call them the basis paths. Different people have different names for these paths. But it's basically the minimum set of paths where I exercise each step at least once, and each decision every way it can go at least once, and I can construct any path by some sort of combinations of these basis paths. So that's the basis paths. It's a subset of all the paths. And when I don't have time to test them all, the subset I like to test is the basis paths. And if I find a bug with the basis path, I would generally find a bug that would block several possible paths through the system. Now, a control flow diagram is not hard to draw. You can use any tool like Visio to put it together, or even PowerPoint. You use circles and lines, right? Just like a flow chart. So you would say you have process steps like A flows to B, B flows to C. We can have loops. So A flows to B flows to C flows back to A. We're allowed loops. We have decisions. A flows to B or A flows to C. We have junctions. C comes from A or C comes from B. And we can do some sort of math on it. There's a equation people use called McCabe's cyclomatic complexity equation, if you want, which is a count of the number of basis paths. It is not voodoo mathematics. It comes from discrete math, what's called graph theory. But to count the number of basis paths, pretty easy. You count the number of circles, that's N, the number of lines, that's E, and then P is just E minus N plus 2, and that gives you the number of basis paths. And this, on slide 22, this diagram doesn't tell you very much because there's only 3 basis paths in it, and there's only 4 paths in all, so it's not a really good example. I'll show you a much stronger example in a minute. The algorithms for finding basis paths have been published. There's one of them that's in Lee Copeland's book, A Practitioner Guide to Test Design. There's a whole chapter about the subject, but it's basically got 5 steps. The first step is you find a typical baseline path. You pick a path. So you pick a path through the system. Then to find the second path, you walk through the first path, but you flip the first decision you come to and keep the rest as similar to the first one as you can. For the third one, you keep flipping decisions on the baseline until you run out of decisions. And then we basically pop off the stack the first alternate one we did, and we go through the decisions on that, continuing until we've exhausted all the paths. This is very tedious to do by hand. I've done it by hand. I can do it for up to about 30 nodes. I recommend people consider tools. There are some commercial tools, and I include in the Dropbox a free tool that we put together with some McGill students and I a couple of years ago to help sort of promote this method. It's not a tool that is very robust, simple, but it basically is tedious to do this by hand for several nodes. So let me share with you my story of how this technique helped us out in a really serious insurance case study. This story took place in Chicago at a major insurance company. I was there on site. I was teaching test design workshops. I was going all over the place teaching test design workshops when suddenly the test manager walks into my teaching room that I was working in, the classroom, It says, Rob, we have an emergency. We have a crisis. And I was called into their war room. I was called into the war room. And I was told, Rob, please help us. So I dropped what I was teaching and I listened to their problem. And they had an interesting problem. In the room, there was the project manager and there was the test manager and there was a domain expert, a guru, a domain subject matter guru. And the three of them explained to me that they had a major project that was now being piloted with about 400 users, 400 of a potential several thousand were piloting it, and it was failing all over the place. It was crashing, it was failing, everything was screwing up. But the application had been very, very thoroughly tested in their normal testing process. They had done tons of what they call functional system testing, tons and tons and tons. And they had, passed to their satisfaction, all of that testing. Then when they deployed the thing into the pilot, it started failing all over the place, and it was beyond themselves, what was going wrong. So I took a look quickly with them, and from a technology perspective, they were doing a migration from mainframe to multi-tier architectures, a big change in architecture, but their testing philosophy wasn't really tuned to multi-tier object-oriented systems. It was more tuned to batch processing mainframe systems. And so their testing methods were missing certain type of bugs. And the bugs that were missing were cross-feature interference bugs, where feature A interfered with feature B, not intentionally, accidentally. So you have features that are accidentally interfering with each other. And so you have this sort of concern that they thoroughly tested all of the features, but the testing was done independently. And so they were confident in the independent features, but they really had no knowledge about how they interacted with each other. So I basically talked to them and I learned a little bit about the system. And I found out that the system had a whole bunch of screens. And these were basically subsystems. And to get to a screen, you basically had 3 pull-down menus. The first pull-down menu, A, had 5 choices. The second B had 6 choices. The third C had 2 choices. So to get to a screen, you took a value from A, B, and C, and it went to a unique screen. So the question, how many screens are there comes up, and it's pretty obvious to me that there's 5 times 6 times 2, there's 60 possible screens, right? And sure enough, that's how many screens that they had, 60 possible screens. And they basically, so to test all the screens thoroughly, they had 60 tests to exercise the screens. But then they realized, okay, now we're not testing for cross-feature interference, so maybe what we should do is start testing the different ways the screens interact with each other. So one way to do that is to look at the permutations. So how many tests would be required to exercise all possible screens in every possible order at least once? So all possible screens in every possible order at least once. And that's basically the question they started talking about. And it works out that if you do the math, that gives you 60 factorial test cases. Now, 60 factorial test cases is basically equal to 60. So you have 60 choices for the first one, 59 for the second, 58 for the third, all the way down to 321. You multiply that out, and you get to this number, which is 8.32 times 10 to the 81. Now, 8.32 times 10 to the 81 is a very, very large number. And this number, in fact, is so large, it's hard for a human being to conceptualize it. And they were saying, well, maybe we should do some automation. And I was trying to tell them, no, automation won't help you in this case. This number is so large that you will never in your lifetime come near even scraping the surface of testing it with all the automations on the planet. If you want to get an idea of how big that number is, take a look at some of the work from NASA, physicists studying the visible universe from the Hubble Space Telescope. They estimate that the number of atoms in the observable universe, the number of atoms in the observable universe is between 10 to the 79 and 10 to the 82. And that means that my customer had wanted to do more test cases than the lower bound of the number of atoms in the visible universe. I'm not joking. This is really what was on the table. It was impossible, ridiculous, absurd, intractable, never doable. But they sort of understood the problem space. So I talked to them a little bit, and I sort of tried to understand what really mattered to them. And learning more about it, I asked them, do they have any descriptions of the workflow of the system? And sure enough, there was a whole training department that was training operators in the workflow of the new system. And so we invited the training department to send someone to the war room crisis management meeting. And they basically showed me and the team, they showed us some of the flow charts that they used to teach people the workflow of this new system. So I looked at this, I discussed it with them, and I said to them, well, this is an interesting, diagram here. What if we tried to find a set of pathways through this workflow that we could exercise to try to expose bugs that are cross-feature interference bugs that show up in real workflows? So it's not every possible one, but the ones that might show up in real workflows. How can we bubble those up? And so I took this, and while in Chicago, in the war room, with everybody there, I drew a control flow diagram. This is a digital photo of the control flow diagram. Now you'll notice that there's a lot of circles in it. There's actually 45 circles in my control flow diagram. It's interesting to note that their system had 60 possible screens, but my control flow diagram had only 45 circles in it. Shouldn't there be 60 circles? Well, the answer is not all screens showed up in the workflows. When we look at the diagram, there's 65 edges, which we do the computation, would give us 22 basis paths. I applied the algorithm from Lee Copeland's book by hand at the customer's site, and I came up with these 22 basis paths. 22 basis paths. Now, they were basically, these are the ones we came up with. Only 22 tests. So not 8 times 10 to the 81 tests, but 22 tests. Now, these 22 tests are an important set. And I told the customer very carefully, I said, you have to get all of these running. You can't just pick your favorite one here, because the value of this is running the whole set. If you run the whole set, so then you will learn a lot. If you only pick and choose from this set, it's not really going to help you very much. So they did, and they took 3 weeks to do this, because they had to, for each path, set up data and transactions to walk through it. And while they walked through the transactional paths, they found all sorts of problems. And they fixed them, and they continued until they could run through flawlessly all 22 paths. The whole process took them about 3 weeks to do. At the end of the 3 weeks, they restarted the pilot, and they were able to go from the pilot to production with no additional software engineering changes to the system. So this, to me, is a beautiful example of the application of control flow test design to a workflow system. When you can't test all possible permutations of all possible operations, and your risks include cross-feature interference, which could be for many reasons, like resource contention problems, data problems, object modeling problems. There's all sorts of technical risks in there. Today, we see more and more of this in microservice architectures, and there's no way you can possibly test all the different paths between all the systems. So finding the workflow gave us a method to model. We used control flow test design, found the paths, and then created tests for each path. One test per path, basically, with specialized test data and test transactions, and fix the bugs, keep going until you can get all 22 running flawlessly, and then they were able to go to production with no additional work. Now, in control flow test design, there's some other interesting things you might want to look at. We can, for example, consider a subset of tests that might be interesting for you. For example, test all nodes at least once. That's a smaller set. or test all edges at least once. That might be a smaller set. Or try to test all paths, which is possible, reasonably possible, if there's no looping. Now, I, with my middle students, put together a simple tool, which we call paths. There's a copy of this tool in the Dropbox if you're interested in trying it. I don't have a lot of people to support it. It's just done by some basically undergrads with me, just to make the point here. It's not a very robust tool, but it does the job, and I'll show you an example here. So what you do is you take your problem. So let's say, if you can imagine, that we have this flow chart on the top here, and we want to find the pathways through this interesting set of pathways. Let's say the basis paths through this flow chart. Now this is easy to do by hand with this case, but just to show you how the tool would work. What you do first of all is you create what's called an edge list. An edge list is just a text file which describes your control flow diagram. So the first line in it is the name of the starting node. The last line in it is the name of the ending node. And then every other line in this text file is the name of an edge. So this edge here is between start and A. This edge is between A and B, between B and D, between D and A, between B and C, between C and end. So that's all there is to it. The tool is run in a batch file. It's just simple command line batch file. It's a Java program, so you need a Java runtime environment to do it. And it will tell you the results of, for example, the basis paths. There's two of them. Start A, B, C, end is one. Start A, B, D, A, B, C, end is the second one. Or if you just want the tests to try all edges once, this would work actually. Start A, B, D, A, B, C, end would try each edge at least once. So this is the different types of things you can pull from the tool. I believe there's a few other command line options in there. I want to show you another example before I stop this little webinar chat here. This one came up last week. It's interesting how control flow problems land on my desk from time to time. And this is from someone who basically had a transaction model of a system, and they had diagrammed it with this sort of picture like this. The little blocks on them, I call them nodes in it, are process elements. And going from start to end, there's many, many different pathways through the system. The question is, can we find a reasonable subset of the pathways through the system to basically exercise the system thoroughly without having to try every single path? And so I took this and I basically said, okay, let's just take this diagram and see if we can apply it to our little tool there. So I'm going to open up my node. So this is the node list I made here. So if you look at the file here, there's 70 lines in it. The first line is the starting node. The last line is the ending node. And there's basically 68 edges in the file, nothing complicated. When we run the program, it's just a Java runtime command line program. So the syntax is very simple. The tool is called paths.jar. The input file is called the Fred nodes input. The output file is Fred basis output or Fred edge output. It's all text files, nothing too complicated about the formats here. If you look at the all edge case, so that would give us, I believe, how many tests? 24 tests. If you run these 24 tests, you will have exercised every edge at least once. Or if you take the basis paths, which is coincidentally also 24, so that doesn't always happen to me, that if you run these, you will have every edge, every step at least once, every branch, every way can go at least once, and you can construct any path by combining these paths. So this is just a little worked out example of a control flow testing problem. They show up all over the place. Control flow testing problems show up in all manners of software testing. And unfortunately, the method of control flow analysis and test design has fallen off of use, mostly because people have promoted it almost completely as a white box testing technique, when I'm a firm advocate that it will work in any system that can be modeled with a control flow diagram. Workflow, process flow, data flow, almost any imaginable flow. So that's what I wanted to talk about. And Chris, I know.
Yeah.
Questions?
Great. Thanks for that. Do you want to flip back over to your instructor slide just so that we have your contact information? If anyone has any questions, go ahead and get those in. We already have a few of them. So it looks like you actually applied this as a black box technique to the UI for your example. And so is that typically, so you sort of said that like it tends to be a black box sold as a white box technique, but you clearly showed it as a black box technique. So how do you know when to apply that? Is that just experience or?
Well, first of all, let's get rid of let's baggage problem. The term white box and black box technique doesn't always help you in testing. So who does it help? I don't know. But years and years ago, people decided to classify testing that way. I think it was a little bit because people were afraid you had to learn programming to use certain techniques. So they sort of said, these are for programmers, these are for non-programmers. Whatever the history is, the distinction between a technique as being white box and black box has not always helped the industry, has not always helped the profession of testers. So yes, it's classified as white box technique because people use it for code, but it can be used for anything that you can draw that picture with. So if I can draw a control flow diagram, I can use this technique. And I can do that for code too, by the way. So I can take code and draw a picture like that, or I can take a workflow and draw a picture like that. I definitely believe that it is perfectly reasonable to use as a black box technique. Absolutely. Testing it at the functional level, not testing at the guts, at the code level. So I agree 100% that I was using it as a black box technique, even though it's been promoted as a white box technique to a disservice, I think, because there's tons of testers who have never even learned about it because it was taught only to programmers who doing unit testing. I don't know if that answered the question. So
yeah, that's
it's not a disconnect. It's just that the technique applies to anything you can draw that picture for. So if you can draw a flow diagram of whatever you're testing, and almost any part of your application you can do that, then it'll help you find pathways through it. If you have like an infinite number, it'll give you a nice subset to help you find important bugs.
Yeah, so that goes, thank you. That sort of goes into the second question we had, which is how do you know when to apply that? And it sounds like you just said if you can sort of illustrate it as a point, as nodes, then you can basically do path analysis, right?
Right. Although I want to always be sensitive to my context, and I do not want to apply this every time just because I can draw the diagram. So the diagram is sort of like, it's important. I have to be able to diagram it, but that's not enough. It also has to make sense. So for example, workflow makes a lot of sense because I'm looking at a system and I'm saying, okay, instead of modeling what the software does for the user, I'm modeling what the user does with the software. And if the user can't do their job with the software, it's useless to them, and therefore it's meaningful to test at the workflow level. So it's not just that I can draw the picture. It also has to make sense from the context. I'm always afraid that people learn a technique like this and they apply it to everything. Well, it applies to a lot of things, but I like to make sure that it's going to be giving you useful information. And you can use it once you know it. You can use it a lot, but make sure that it fits the type of knowledge you're looking for when you're testing the application.
Great. A few people have said that they can't find the chat panel, and so where we posted the slides. So hopefully you can find that in the GoToWebinar software that's on the side of your computer. Sometimes you have to actually expand it. But if you can't actually find the Dropbox link, that's okay, because so it's a Dropbox link, and even if you can't find it in the chat channel now, we're going to email that to everyone. Since you've all registered, you're going to go ahead and get it. So don't worry too much about that. So that's sort of going back to Rob's last point. So what are the strengths and weaknesses of this technique? Like, when is it good to apply and when is it not? Can you shed some light on that in your experience?
Okay, well, it's funny. People ask me that type of question a lot, and my answer is that I look at what is the best problem solving technique to use at the time, and so I certainly can tell you that some problems are combinatorics problems where I'm trying to find outliers. And if I'm looking for outliers, I wouldn't use this control flow approach. I would use probably something like a pairwise combinatorics approach to do things. So if I'm looking for outliers or weird situations, if I'm looking for platform compatibility bugs, I probably wouldn't use a path analysis approach. I would probably use a different approach. I look at my Swiss Army knife and I'm trying to say, because your question is saying, is there times when I don't want to use the tweezers? Yeah, I don't want to use the tweezers if I'm not pulling something out, right? I don't want to use the saw blade when I'm not cutting a piece of wood. So I basically say that if the path analysis tool is one blade, if there's a better blade to use that blade. So look at the problem and choose the appropriate blade. I will say though that sometimes when you're testing, you're looking for sort of bugs that are weird circumstances that are going to be hard to replicate in the field. I don't think that path analysis would necessarily help you with that. I think there's other combinations test design techniques that would help you with those.
Excellent. And so it seems like there's a lot of interest in being able to use the tool that you provided. Are there, and maybe you know this, maybe you don't, but are there good places to sort of practice? Like if people download and want to use the tool, do you know if there are good example sites or is there something you can recommend for someone to try?
I have in the Dropbox, I put a few example of input files to it. The tool is not terribly robust, so I basically I encourage you to use it, but its input error handling is really weak. So you might be, if you're used to commercial tools which are robust, you'll have more fun with it. But I throw some examples in there. I think you want to start with a problem that you can solve by hand. So for me, that would mean for me, it's less than 32 nodes is what I can do by hand. For someone who's just starting, take a look at solving a problem with, let's say, between 10 and 20 nodes. That size would be a good size to experiment with. And I would take the algorithm as published in Lee Copeland's book or any source you want. But Lee's book, I think, has the best description of it, A Practitioner's Guide to Test Design. And try the algorithm and solve the problem with the algorithm and then use the tool and see if you get comparable results. So I would try with smaller things, 10, 20 node size, and try the algorithm by hand, and then try the tool to see if you get comparable results. Because I want you to sort of learn the technique by understanding what the tool's trying to do, not just by taking the tool to do all the work for you. I mean, it's going to help you, especially if you have a lot of nodes.
Yep, that's a great point. Got to know how to use the technique before using the tool. And so you actually sort of answered the next question, which was, do you have any references or anything for learning more about path?
Yeah. Lee's book is a great reference on it. And in fact, I'm going to put a scan of the cover of that book in the Dropbox right after this session, so that people have it. But his book is A Practitioner's Guide to Test Design, and each chapter of that book teaches a different test design technique, and nothing in there is technology specific or project specific or life cycle specific. It's really just focused on different test design techniques, and so few books about testing do that. So that's my sort of go-to reference for a nice description of control flow test design.
Okay. So someone says, Andrew says, I like the fact that the control flow helps us look at what users might do and shift away from pure functionality. But from a tester's point of view, it's often easier to get access to functionality information over usage information. In your example, the usage information was probably the the domain expert, everyone in the war room, basically, including the trainer, I think it was.
Actually, the person who had the information was not in the room. The people who were subject matter experts had no idea of how users use the system. Subject matter expertise doesn't mean they know anything about users. This is a myth in the industry that subject matter experts can know how to model users. Subject matter experts know how to model the domain. They're really good at the case I was at insurance, at actuarial analysis, at the risk tables, and all the complicated things. They wouldn't know the life of an operator for an insurance application if you paid them. So what we did there was we basically got the training people in the room, but it was because I asked the question: is there a description of the workflow? They hadn't ever asked that question. So if I was a tester and I was in a project, I would look for many different types of test ideas. Not just functional testing. You have functional testing, capabilities, failure modes, usage scenarios, quality factors. There's all sorts of different types of testing ideas. And I would hunt like a truffle snorting pig, stick my nose everywhere to try to find information about them. They come from the least likely places. And in my case, it was the training department in Chicago that had the key to unlock the testing problem. That wasn't even on the list of testers or business people. And I've often seen cases like that where there's fantastic insights into how we might consider testing something that is just not in your normal requirement documentation. And it gets worse in Agile teams. You might think Agile's better at this, but actually Agile teams are so focused on a small amount of functionality in a small amount of time, they don't have the big picture at all in there. And sometimes when you're under the gun, you want to sort of look at the big picture and say, how can I say something reasonable about the big picture instead of saying something really detailed about a small part of the picture? So my advice to people is to stick your nose in all sorts of places to try to find insights into where you can get testing ideas that are not just the functional stuff. However, if you're only stuck with the functional information, you're right. I don't want you to make this up. You can't invent workflow. You have to actually look at how users use systems and somehow have some way to model that. Maybe a skill you could develop is called a task analysis skill, which if you look at the stuff that Dr. Kainer used to teach in the workshop on software testing, is basically a method to learn about the workflow through interviews and stuff like that. But still, you have to interview people to get the data, right? So it's sometimes you just don't have access to it. And I agree that if you don't have access to it, a path analysis like this probably is not going to be too useful.
All right. I think that's all the questions we have, unless anyone else wants to get one in last minute. Otherwise, I'm going to say thank you to Rob. Rob, did you have anything else that you wanted to say?
No, I wanted just to remind people that this webinar and all my other stuff always comes with a lifetime guarantee, which is my life, not yours. So I hope you're interested in me having as long a life as possible. If you ever have questions or concerns, or you want to dabble with the space of control flow testing, send me an email. I'll be delighted to get you examples, case studies, answer your questions. I'm there to help.
Great. So thank you to Rob, and thank you to everyone else for joining. That concludes this presentation. Thanks, everyone.
All right. Bye. Thank you.